Hi everyone, today I'm presenting a 4-bit 2-to-1 multiplexer designed in quarter span. Looking at the schematic, the circuit uses 8 AND gates and 4 OR gates. These are organized into 4 identical channels, one for each bit. For every bit, a pair of AND gates acts as a switch, controlled by the ALU cell 1 signal, and an inverter to select between input S and P. The logic is simple. When ALU cell 1 is 0, the output M matches input S. When ALU cell 1 is 1, the output M switches to match input P. We can verify this in a simulation. At 10 nanoseconds, LU cell 1 goes high, and output M correctly follows input T, which is 0, 0, 0, 0. At 30 nanoseconds, T changes to 1, 1, 1, 1, and input M updates immediately. Finally, at 50 nanoseconds, the select signal drops to low, and the output instantly switches back to match input S, which is 0, 1, 0, 1. Now, I'm demonstrating a full adder circuit. This circuit takes 3 binary inputs, A, B, and carry in, C in, and calculate the sum S and carry out, C out. Looking at the schematic, the logic is split into two parts. The sum is generated by two cascaded XOR gates representing the equation A XOR B XOR C in. The carry out uses two AND gates and an OR gate to detect if at least two inputs are high, following the logic AB plus C times A XOR B. Now I'm demonstrating a 4-bit ripple carry adder subtractor designed in quarters. This circuit uses 4 full adders and XOR gate to perform two complements arithmetic. The control signal K determines the mode. When K is 0, the circuit adds. When K is 1, it performs subtraction by inverting input B and adding a carry in of 1. Now let's look at the functional simulation. In the first 100 nanoseconds, A is 0 and B is 0, 0, 0, 1. With K at logic low, the output S is 0, 0, 0, 1. This confirms correct addition. At 100 nanoseconds, K toggles high. Now A is 0, 0, 0, 1 and B is 0, 0, 0, 1. The circuit performs 1 minus 1, resulting in an output S of 0. Looking further down, at 300 nanoseconds, K returns to 0. A is 0, 0, 1, 1. Decimal 3 and B is 0, 0, 0, 1, decimal 1, giving us a sum of 0, 1, 0, 0, decimal 4. Now, I'm demonstrating a 4-bit register design using D flip-flops. This circuit is the fundamental building blocks for data storage, capturing a 4-bit input M and holding it at the output ALU out based on the clock signals. Looking at the waveform, notice that at the beginning, while the RST signal is high, the output ALU out is forced to 0 because we have a NOT gate on the reset line in the schematic. The register clears when the input RST is high. When RST goes low, the register becomes active. On the next rising edge of the clock, the input value 0011 is sampled and successfully latched to the output. Observe that between clock pulses, even if the input M changes, the output stays stable. It only updates exactly at the rising edge of the clock, such as at 400 nanoseconds and 500 nanoseconds. Now, I'm presenting a 4-bit ALU built in quarters. This circuit integrates a ripple carry adder subtractor and an XOR XNOR logic block. Use a multiplexer to choose which operations result reaches the output M. Now, looking at the functional simulation, ALU cell 0 controls the internal adder mode, while ALU cell 1 acts as the mux selector. At the start, when ALU cell 1 is low, the mux picks the result from the adder. For example, with A equals to 0 and B equals to 2, the output M is 0, 0, 1, 2. When LU cell 1 toggles high at 25 nanoseconds, the mux switches to the logic block. Now, the output M changes to 1, 1, 0, 0, which is the XNOR result of the inputs. At 40 nanoseconds, we see the output update again as input changes, demonstrating the real-time processing of the selected data path. Now, I'm demonstrating a 4-bit LU system in quarters. This design integrates selection, computation, and storage. It is the core of a simple processor data path handling both arithmetic and logic tasks. Let's look at the internal logic. Input selectors. This multiplexer uses A cell and B cell signals to choose which 4-bit word enters the LU block, the heart of the circuit. It contains a ripple carry adder for arithmetic and an XOR XNOR block for logic controlled by the LU cell lines. Register. These D flip-flops acts as a memory, capturing the final result precisely on the rising edge of the clock to ensure stable data output. First, observe the reset signal. While reset is high, the LU out is forced to 0, proving our synchronous clear is working. At the 200 mark, reset drops, and the circuit becomes active on the next rising edge of the clock. Notice the transition at 300 nanoseconds. A cell is 0, 0, and B cell is 0, 1. The LU cell is set to 1, 1. We see the LU out change to 1, 1, 1, 1. As we move across the timeline, you can see the propagation delay. The inputs change slightly before the clock edge, but the output LU out only updates precisely precisely at the rising edge of the clock. This confirms that our registers block is successfully capturing the LCU combinational results and holding them steady for the next cycle. Thanks for watching.